In Cartesian coordinates, the unit vectors point the same way at every point in space. In cylindrical coordinates, they don't. Move to a new location, and the unit vectors rotate with you. This single difference shapes how we describe motion in physics. We'll build both systems from scratch. Physics studies phenomena we observe in the world. To connect those observations to mathematics, we need a coordinate system. Every coordinate system has four basic elements. First, a choice of origin. Second, a choice of axis. Third, a choice of positive direction for each axis. Fourth, a choice of unit vectors at every point in space. Three systems appear most often: Cartesian, cylindrical, and spherical. We'll construct the first two. Notice that element 4 says unit vectors at every point. That detail matters more than it seems. Start with the Cartesian system. Choose mutually perpendicular axes that intersect at a common point, the origin O. Since we live in three spatial dimensions, we use three axes. The x-axis, the y-axis, and the z-axis all at right angles. Each point P in space then gets a triplet of values: x sub P, y sub P, z sub P. Each coordinate ranges from negative infinity to positive infinity. Place the origin wherever it's most convenient and assign positive directions freely. A problem that's difficult with conventional choices can become much easier with a thoughtful choice of axes. Now the fourth element. At each point P, attach three unit vectors: I hat sub P, J hat sub P, and K hat sub P. Each has magnitude 1. The vector I hat points in the direction of increasing x at point P. Similarly, J hat points towards increasing y, and K hat towards increasing z. Pick a different point S and define its unit vectors the same way. The result: I hat at S equals I hat at P, J hat at S equals J hat at P, and K hat at S equals K hat at P. Two vectors are equal whenever they share direction and magnitude, regardless of where they sit. Because this equality holds everywhere, we drop the point labels and write simply I hat, J hat, K hat. Cartesian is the only coordinate system where this works. Other systems exploit symmetry instead. Rotate a uniform cylinder about its longitudinal axis, and it looks unchanged. That rotation is a symmetry operation, and it suggests the cylindrical coordinate system. Choose an origin O and an axis through it, the z-axis. The cylindrical coordinates of a point P are three numbers: r, theta, and z. Here, z is the familiar coordinate along the z-axis. The non-negative number r is the distance from the z-axis to P. Points with constant positive r form a circular cylinder. Points with r equal to 0 form the z-axis itself. The angle theta needs a careful construction. In the plane where z equals 0, define a reference ray through the origin, the positive x-axis. Draw a line through P parallel to the z-axis. Call D the point where that line meets the z equals 0 plane. Draw the ray from O to D. Theta is the directed angle from the reference ray to ray OD. It's positive measured counterclockwise, negative measured clockwise. The pair r and theta are called polar coordinates. Polar and Cartesian coordinates convert directly. Given r and theta, the Cartesian coordinates are s equals r cosine theta and y equals r sine theta. The geometry is a right triangle. R is the hypotenuse. Theta is the angle measured from the x-axis, so the adjacent side gives x and the opposite side gives y. Going the other way, given x and y, we recover r as the positive square root of x squared plus y squared. That's just the Pythagorean theorem. And we recover theta as the inverse tangent of y over x, since the tangent of theta equals opposite over adjacent. Let's check a quick case. Take r equals 2 and theta equals 60 degrees. Then x equals 2 times 1/2, which is 1. And y equals 2 times the square root of 3 over 2, which simplifies to the square root of 3. Now the unit vectors at point P, choose r hat, theta hat, and k hat. The vector k hat points toward increasing z, just as before. The vector r hat points toward increasing r radially away from the z-axis. The vector theta hat points toward increasing theta, counterclockwise, tangent to the circle through P. Here's the crucial difference from Cartesian coordinates. These directions depend on location. At a different point, S r hat at S points radially outward from S's position, a different direction entirely. So r hat at P does not equal r hat at S, and the theta hat at P does not equal theta hat at S. By convention, we still drop the subscripts and write r hat, theta hat, k hat, keeping in mind that the directions of r hat and theta hat depend on where the point is. At any point P, the polar unit vectors decompose into Cartesian components. The vector r hat equals cosine theta times I hat plus sine theta times j hat. The vector theta hat equals negative sin theta times I hat plus cosine theta times j hat. Let's check it. Each has magnitude 1 since cosine squared plus sin squared equals 1, and their dot product vanishes, so they stay perpendicular. Now for the inverse transformations. The vector I hat equals cosine theta times r hat minus sine theta times theta hat, and the vector j hat equals sin theta times r hat plus cosine theta times theta hat. Cylindrical coordinates shine when an object moves in a circle about a central point. Place a vertical axis through that point, perpendicular to the plane of motion. Any rotation about this axis leaves the circles unchanged, so the description simplifies. The core lesson: every coordinate system needs an origin, axis, positive directions, and unit vectors. Cartesian unit vectors are identical everywhere in space. Cylindrical unit vectors r hat and theta hat rotate with position, linked to Cartesian by x equals r cosine theta and y equals r sin theta. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.